What if everything, every galaxy, every star, every atom in your body is slowly turning around something you can't see? Not spinning like a planet, not orbiting like Earth around the sun, but rotating in a deeper, more unsettling way where space itself is doing the turning. Right now you feel still. The ground beneath you feels solid, unmoving, but you are already moving through space at thousands of kilometers per hour. Earth spins, it orbits, the sun moves through the galaxy drifts through the cosmic web. So here's the real question. What if this motion doesn't stop there? What if the entire universe is rotating and we're inside it? And if that's true, what is it rotating around? Physics begins with something deceptively simple. Motion only makes sense relative to something else. A train moves relative to the ground. The Earth spins relative to distant stars. Even rotation, which feels absolute, can be detected through forces like the outward pull you feel on a spinning ride. But now remove everything external. Imagine a universe with nothing outside it, no backdrop, no reference frame, just space, matter, and time all contained within itself. Can such a universe rotate? This question isn't philosophical decoration. It sits at the heart of modern physics, especially within the framework of general relativity developed by Albert Einstein. Einstein replaced the idea of gravity as a force with something stranger. Space and time are not passive. They bend, stretch, and respond to matter and energy. Massive objects curve space-time, and that curvature tells matter how to move. But curvature is not the only thing space-time can do. It can also twist. In certain exact solutions of Einstein's equations, space-time develops a kind of rotational structure. Not just objects moving within space, but space itself having a built-in sense of rotation. This is not like a whirlpool inside a river. The river itself becomes the whirlpool. One of the most famous of these solutions came from Kurt Gödel in 1949. Gödel constructed a universe that rotates globally, not approximately, not locally, completely. And in doing so, he revealed something deeply unsettling. In his rotating universe, time does not behave the way we expect. The structure of spacetime allows paths that loop back on themselves. These are called closed time-like curves, trajectories where an object can travel forward in time and yet arrive at its own past. No exotic matter, no wormholes, no violations of Einstein's equations, just rotation. This is where the idea stops being abstract and becomes dangerous. Because if rotation of the universe is even slightly real, then causality, the simple idea that cause comes before effect, may not be as fundamental as we believe. But before going that far, we need to understand something more basic. What would rotation of the universe actually look like from the inside? If you stand on Earth, you can detect rotation, not by looking outward, but by measuring forces. A spinning object creates centrifugal effects, water bulges at the equator, air currents deflect, pendulums shift direction over time. This is not illusion. Rotation has physical consequences. Now scale that idea up. If the universe were rotating, there should be subtle signatures imprinted across everything. Light traveling through space might be slightly deflected depending on direction. Large-scale structures, clusters of galaxies, might show preferred alignments. There could be an axis, a cosmic direction that is physically meaningful. This brings us to one of the most important observational tools in cosmology, the cosmic microwave background. This radiation is ancient. It comes from a time when the universe was only about 380,000 years old, a fraction of its current age. Before that, the universe was opaque, filled with a hot plasma where light could not travel freely. But as it cooled, atoms formed, and light began to move unhindered. That light is still here. It fills the universe in every direction, almost perfectly uniform, like a faint afterglow of creation itself. If the universe had a strong global rotation, it would leave an imprint on this radiation. Not random noise, but a systematic pattern, an asymmetry, a preferred axis. Scientists have looked for this. Carefully, repeatedly, using satellites and precise measurements. And what they find is this. The universe is remarkably isotropic. It looks the same in all directions to a very high degree of precision. No obvious rotation. But no obvious rotation is not the same as no rotation at all, because physics rarely deals in absolutes, it deals in limits. Current observations place extremely tight constraints on how much the universe could be rotating. If it is rotating, it must be incredibly slow, so slow that its effects are buried within the noise of cosmic measurements. And that opens a door. Because even a tiny rotation over billions of years and across unimaginable distances could shape the structure of reality in subtle ways. There have been hints, controversial, debated, not fully accepted, that certain large-scale alignments in galaxy spins might not be entirely random. Some studies suggest a slight coherence, as if something is biasing direction on a cosmic scale. These results are not settled. Many physicists remain skeptical. The data is difficult, the interpretations uncertain. But the possibility remains. And in physics, a possibility that refuses to disappear is often more important than a conclusion. Now consider a deeper layer of the problem. If the universe rotates, what defines the axis? In everyday rotation, the axis is defined relative to external space. A spinning top rotates relative to the room. The Earth rotates relative to distant stars. But if the universe includes all of space, there is no external reference. So where does the axis come from? This question connects to an old and subtle idea sometimes associated with Mach's principle, the notion that local motion, including rotation, is somehow determined by the distribution of mass in the universe. In simple terms, the universe itself defines what it means to rotate. And Einstein was influenced by this idea, though his theory does not fully implement it. In general relativity, rotation can exist even in otherwise empty solutions. Space-time can have properties that are not entirely dictated by matter alone. Gödel's universe is a perfect example. It rotates not because of something outside it, but because the geometry of space-time allows it. And this shifts the perspective entirely. Rotation is no longer about motion within space. It becomes a property of space. And once you accept that, a new question emerges. If space-time can rotate, can we detect that rotation not by looking outward, but by examining the behavior of time itself? Because in a rotating space-time, time does not flow uniformly in all directions. The structure of causality can tilt, bend, and in extreme cases, loop. This is not speculation, it is a direct consequence of Einstein's equations, and it leads to one of the strangest possibilities in all of physics, that the large-scale motion of the universe could influence the very nature of time. Pause here and think carefully. We started with a simple idea, maybe the universe is rotating. We followed it into the mathematics of space-time, and now we're at the edge of something much deeper, where motion, geometry, and time are no longer separate concepts, but different aspects of the same underlying structure. The question is no longer just, is the universe rotating? It becomes, if it is, what does that mean for reality itself? The idea that rotation could reshape time itself sounds extreme, but in relativity, time is not a universal background ticking the same way everywhere. It is woven into space-time, and its behavior depends on geometry. To see why rotation matters, imagine light traveling through space. In ordinary conditions, light follows the straightest possible paths, what physicists call geodesics. But if space-time is curved, those paths bend. This is how gravity works in general relativity. Mass tells space-time how to curve, and curved space-time tells light how to move. Now add rotation. When space-time rotates, it doesn't just curve paths, it drags them. This effect is known as frame dragging. Around a rotating object, space-time is literally pulled along with the rotation, like honey being stirred. This is not theoretical speculation. It has been measured around Earth and around massive rotating bodies like neutron stars. The effect is small near Earth, but it becomes stronger near denser, faster spinning objects. But what happens if this dragging is not local, but global? If the entire universe had even a slight rotational component, then every path, every beam of light, every particle trajectory would be subtly influenced by that rotation. Not enough to be obvious in everyday experience, but enough to accumulate over cosmic distances. Light coming from opposite directions might not be perfectly symmetrical. Time intervals might depend ever so slightly on direction. The universe would have a hidden bias, a preferred orientation embedded in its structure. And here is where things become even more subtle. In a rotating space-time, the distinction between space and time can begin to blur in unexpected ways. Normally, we separate directions into spatial ones, left-right, up-down, and one temporal direction, forward in time. But relativity allows these distinctions to shift depending on motion and geometry. Gödel's solution pushes this to the extreme. In his rotating universe, the geometry tilts the structure of time so much that certain paths, if followed carefully, loop back to their starting point in time. Not by reversing direction, not by breaking physical laws, but by continuously moving forward along a path that curves through spacetime in just the right way. This is what creates closed time-like curves, and it raises a disturbing possibility. The universe might not forbid journeys into the past. Most physicists are uncomfortable with this, not because it is mathematically inconsistent, it isn't, but because it challenges causality. If you can return to your own past, you can interfere with the chain of cause and effect. There are ideas to prevent this. Some suggest that quantum effects would destroy such paths before they become usable. Others propose that the initial conditions of the universe simply do not allow this kind of rotation. But there is no universally accepted resolution. The equations themselves remain silent. At this point, it's natural to ask, if such dramatic consequences are possible, why don't we see any evidence? The answer lies in scale and precision. The universe is vast beyond comprehension, and its signals are faint. To detect global rotation, we rely on patterns that span billions of light years. Tiny deviations can be masked by noise, by local motions, or by the complexity of cosmic structure. The most powerful probe we have remains the cosmic microwave background. This radiation is not perfectly uniform. It has tiny fluctuations, variations in temperature at the level of 1 part in 100,000. These fluctuations encode information about the early universe, its geometry, and its evolution. If there were a significant global rotation, it would imprint a characteristic signature onto these fluctuations. Specifically, it would introduce anisotropies, differences depending on direction that cannot be explained by random processes alone. So far, the data shows remarkable symmetry. But there have been anomalies, small, persistent features that do not fit perfectly within the standard cosmological model. Some researchers have pointed to alignments in these fluctuations, sometimes called a preferred axis, or even informally, an axis of evil. These features are controversial. They may be statistical flukes. They may arise from foreground contamination or measurement artifacts. Or they may hint at something deeper. A slight global rotation is one of the possibilities that has been explored, though it is far from confirmed. This is where the scientific process becomes important. Physics doesn't jump to conclusions based on intriguing hints. It demands consistency, reproducibility, and independent verification. And so, the question remains open. Now consider a different angle, not observational, but conceptual. What would it mean for the universe to rotate if there is nothing outside it? In classical physics, rotation is absolute in a specific sense. Even in an otherwise empty universe, a rotating object experiences forces. This was demonstrated by Newton's famous bucket experiment. Spinning water climbs the sides of a bucket, indicating rotation even without external references. Einstein challenged aspects of this idea, suggesting that rotation might be tied to the distribution of mass in the universe. But general relativity ultimately allows for both perspectives. Space-time itself can carry information about rotation. This leads to a subtle but profound shift. Rotation does not need an external reference frame. It can be encoded internally in the geometry of space-time. So when we ask, what is the universe rotating relative to, the answer may be nothing external. The rotation is a property of the universe itself. Like curvature, it does not need a background. It is the background. There is another consequence, often overlooked. If the universe rotates, even slightly, it introduces a kind of global asymmetry, not in the obvious sense of left versus right, but in the deeper structure of space-time. Physics, at its most fundamental level, is surprisingly symmetric. The laws do not prefer one direction over another. They do not single out a special place or orientation. A rotating universe would break that symmetry. It would introduce a preferred axis, not imposed from outside, but emerging from the structure of space-time itself. This has implications for everything from the distribution of galaxies to the behavior of fundamental particles, though the effects would likely be extremely small. But small does not mean irrelevant. In cosmology, tiny initial asymmetries can grow into large-scale structures. The entire cosmic web, galaxies, clusters, filaments, arose from minute fluctuations in the early universe. So even a slight rotational bias, present from the beginning, could influence the architecture of the cosmos. Now we move into a deeper layer, one that connects rotation with the origin of the universe itself. In the standard cosmological model, the universe begins in a hot, dense state and expands. This expansion is remarkably uniform, with only small deviations, but the model does not fully explain why the universe started the way it did, why these initial conditions, why this level of symmetry, why this particular distribution of energy. Some alternative models consider the possibility that the universe began with a small amount of rotation. If so, that rotation would not necessarily disappear. It could be diluted by expansion, becoming weaker over time, but still present in principle. This is similar to how initial density fluctuations evolve. They start small and grow into galaxies. Rotation, however, would tend to spread out, becoming harder to detect as the universe expands. This could explain why we do not see strong evidence today, even if rotation existed in the early universe. But this is speculative territory. The challenge is to connect these ideas with observations in a precise, testable way. There is one more layer to consider before going further. So far, we have treated rotation as a geometrical property of spacetime. But physics, at its deepest level, is not only about geometry, it is also about quantum behavior. And here, the question becomes even subtler. If space-time itself can rotate, what does that mean in a quantum context? Does the quantum vacuum, the underlying state from which particles emerge, carry information about rotation? Could quantum fluctuations be influenced by a global twist in spacetime? These questions push us toward the boundary between cosmology and quantum gravity, a domain where our current theories are incomplete. We do not yet have a full theory that unifies quantum mechanics with general relativity, and without it, our understanding of the universe at its most fundamental level remains partial. But that does not stop us from exploring the implications, because even without a complete theory, the mathematics we have already suggests that rotation, geometry, and time are deeply connected. And that connection may hold clues about the nature of reality itself. We have moved from a simple question, does the universe rotate, to a network of ideas involving space-time geometry, causality, observation, and the limits of current theory. And yet, we are still only at the surface, because there is a deeper question hiding beneath all of this. Not just whether the universe rotates, but whether rotation is something we can ever truly define in a universe that contains everything. If rotation is not something we can define relative to an external background, then the only way to understand it is through its internal consequences, not by asking what the universe is spinning around, but by asking how such a spin would reshape the behavior of everything inside it. One of the most precise ways to probe this is through light. Light is not just illumination, it is a messenger that carries the structure of space-time across enormous distances. When we observe distant galaxies, we are not just seeing objects, we are reading the geometry of the universe written into the paths that light has taken. In a non-rotating, isotropic universe, light propagates symmetrically. If you send two beams in opposite directions, their behavior, on large scales, should be statistically identical. But introduce rotation, even infinitesimally, and this symmetry breaks. The paths of light begin to depend on direction. Not dramatically, but measurably in principle. Over billions of light years, a tiny bias compounds. One direction might subtly stretch wavelengths differently. Another might alter polarization patterns. These are not effects you would notice locally, but across the full sky, they could leave fingerprints. This is why cosmologists analyze not just the intensity of the cosmic microwave background, but its polarization, how the light waves are oriented. Polarization patterns are sensitive to the geometry of spacetime, including any global twisting. So far, the polarization data aligns well with a universe that is not rotating in any significant way. But again, not significant is not zero. The precision required to completely rule out all rotation is extraordinarily high, and we are still improving those measurements. There is another observational route, one that involves not ancient light, but the distribution of matter itself. Galaxies are not randomly oriented. Each one has a spin, a direction in which it rotates. In a perfectly isotropic universe, these spins should be randomly distributed with no large-scale pattern. Yet some analyses have suggested slight alignments over vast distances, not enough to rewrite cosmology, but enough to raise eyebrows. If such alignments are real and not artifacts of data or selection bias, they could hint at an underlying directional influence, something that subtly organizes motion across the cosmos. A global rotation is one candidate explanation, but caution is essential here. The universe is noisy. Structures form through complex processes involving gravity, dark matter, and initial fluctuations. Extracting a clean signal of global rotation from this complexity is extremely difficult. Still, the question persists because the consequences are too profound to ignore. Now consider a more technical perspective. In general relativity, rotation is encoded in the properties of spacetime through quantities related to vorticity. This is not vorticity in the everyday sense of swirling fluids, but an abstract measure of how local inertial frames twist relative to one another. In a rotating spacetime, if you transport a vector around a closed loop, it does not return to its original orientation. This is a geometric manifestation of rotation, one that does not depend on external reference points. This kind of behavior is deeply tied to the structure of the metric, the mathematical object that defines distances and intervals in spacetime. Gödel's solution is one explicit example where this vorticity is non-zero everywhere, but it is not the only one. There exist families of cosmological models, less extreme than Gödel's, that allow for small rotational components while remaining broadly consistent with observations. These models modify the standard assumptions of cosmology, which typically include homogeneity, the universe looks the same everywhere, and isotropy, the universe looks the same in all directions. Introducing rotation breaks isotropy, but can preserve homogeneity in a generalized sense. This leads to what are known as anisotropic cosmological models. In these models, expansion can occur at slightly different rates in different directions. Rotation can coexist with expansion, though the dynamics become more complex. The equations governing such universes are still derived from general relativity, but with fewer symmetry constraints. What emerges is a richer set of possibilities, universes that are not perfectly uniform, but still governed by the same fundamental laws. There is an important physical intuition to build here. Expansion and rotation are not mutually exclusive. Think of a rotating disk that is also stretching outward. Points on the disk move away from each other while simultaneously circling around the center. The motion is a combination of radial expansion and angular rotation. Now remove the center. In a cosmological context, there is no central point of expansion. Every point sees every other point moving away,
which is a hallmark of the expanding universe. If rotation is present, it must be distributed in a way that does not single out a unique center in the usual sense. This requires a more subtle structure, one where rotation is embedded in the geometry itself rather than around a fixed point in space. Such configurations are mathematically possible, though they are tightly constrained by observations. At this stage, it is worth addressing a common misconception. When people imagine a rotating universe, they often picture something like a spinning sphere in empty space, but this image is misleading because it assumes an external viewpoint. There is no outside from which to watch the universe spin. All measurements must be made internally. All effects must be inferred from relationships between objects and fields within the universe. This is why the question of rotation becomes so abstract. It is not about visualizing motion in a larger space. It is about detecting subtle asymmetries in the behavior of physics itself. Now we move toward a deeper and more speculative layer, one that connects rotation with the nature of inertia. In everyday experience, inertia is the tendency of objects to resist changes in motion. But in relativity, inertia is linked to the structure of spacetime. Objects follow geodesics not because of a force in the traditional sense, but because that is the natural motion in curved spacetime. If spacetime has a global rotational component, then local inertial frames, the local non-accelerating reference frames, would be influenced by that rotation. This connects back to the earlier idea that rotation might be defined by the universe itself. In a rotating cosmos, the very definition of not rotating becomes tied to the large-scale structure of spacetime. Local experiments, like gyroscopes, could, in principle, detect this by showing tiny deviations over long periods. Experiments like Gravity Probe B have measured frame dragging around Earth, confirming that local rotation affects spacetime. Extending this idea to the entire universe is conceptually straightforward, but practically far more challenging. Because the signal, if it exists, is incredibly small. There is one final direction to push this idea further.
If rotation affects spacetime, and spacetime governs the motion of everything, then rotation could, in principle, influence not just large-scale structures, but also the behavior of fundamental fields. Consider the quantum vacuum, the lowest energy state of all fields. It is not empty, but filled with fluctuations. These fluctuations give rise to particles, forces, and interactions. If the background spacetime has a rotational structure, even a slight one, it could imprint subtle anisotropies on these fluctuations. Over cosmic time, these tiny effects could accumulate, shaping patterns in ways we do not yet fully understand. This is where cosmology meets the frontier of quantum gravity. We do not yet have a complete theory that describes how quantum fields behave in a fully dynamic, possibly rotating spacetime at all scales. But we can explore approximations, and those approximations suggest that geometry matters deeply. Rotation is not just motion, it is information embedded in the structure of reality. At this point, the question has transformed. We are no longer simply asking whether the universe rotates, we're asking whether the fabric of spacetime carries a hidden twist, one that influences light, matter, time, and possibly even the quantum vacuum itself. And if such a twist exists, even at a level we can barely detect, it would mean that the universe is not perfectly symmetric. It would have a direction, not imposed from outside, but arising from within its own structure. If a direction exists, if the universe carries even the slightest built-in orientation, then something fundamental changes in how we interpret the laws of physics. Because most of modern physics is built on symmetry. Symmetry is not just aesthetic, it is structural. It tells us which quantities are conserved, which processes are allowed, and how different observers relate to each other. The assumption that the universe has no preferred direction is deeply embedded in cosmology, forming part of what is often called the cosmological principle. Break that assumption, even slightly, and the consequences ripple outward. A rotating universe does exactly that. It introduces a preferred axis, not something you can point to directly, but something that exists in the relationships between measurements.
It means that if you perform the same experiment in different directions, the results might not be perfectly identical at the most precise level. This is not about large, obvious differences. It is about subtle deviations, tiny asymmetries that only appear when measurements become extremely refined. And this leads to a powerful idea. Instead of trying to observe rotation directly, we can search for violations of perfect symmetry. One place to look is in the behavior of fundamental particles. At first glance, particle physics seems far removed from cosmology. It deals with the smallest scales, while cosmology deals with the largest. But the two are deeply connected because the early universe set the conditions under which all particles and forces evolved. If the universe had a rotational component in its earliest moments, it could have influenced how symmetries broke as the universe cooled. These symmetry breakings are responsible for distinguishing forces, generating particle masses, and shaping the structure of matter. A tiny initial asymmetry could, in principle, bias certain processes. Not enough to dominate physics, but enough to leave faint traces, subtle directional dependencies that persist even today. So far, no definitive evidence of such directional effects has been confirmed in particle physics. Experiments are extraordinarily precise, and they have not revealed a preferred spatial direction in fundamental interactions. But the absence of evidence at current precision does not fully eliminate the possibility. It only constrains how strong such effects could be. Now shift focus to gravity itself. Gravity is the dominant force on cosmic scales, and it is entirely described at present by general relativity. Within this framework, rotation is not just allowed, it is natural. Rotating solutions appear in many contexts. For example, rotating black holes are described by the Kerr solution, where spacetime is dragged around the rotating mass. This dragging becomes so extreme near the black hole that no object can remain stationary relative to distant observers. This tells us something important. Rotation is not an exotic feature added to spacetime. It is a fundamental aspect that emerges whenever angular momentum is present. Now extend that intuition to the entire universe. If the universe possesses any net angular momentum, then rotation is not optional. It must be reflected in the structure of spacetime. The challenge is determining whether such a net angular momentum exists. In standard cosmology, the universe is assumed to have zero net rotation. This assumption is not derived from first principles. It is chosen because it fits observations and simplifies the equations. But nature is not obligated to choose the simplest option. There is another layer of reasoning that comes from thermodynamics. In many physical systems, rotation can emerge naturally from initial conditions, especially when small fluctuations are amplified over time. Turbulence in fluids, the formation of galaxies, and the spin of celestial objects often arise from tiny asymmetries that grow.
The early universe was not perfectly smooth. It contained fluctuations, variations in density and energy that eventually led to galaxies and clusters. Could similar fluctuations have produced a small but non-zero global rotation? The difficulty is that rotation behaves differently from density fluctuations. Expansion tends to dilute rotation. As the universe grows, any initial rotational motion spreads out, becoming weaker and harder to detect. This means that even if the universe started with a noticeable rotation, it could appear almost perfectly non-rotating today. This is a crucial point. The absence of strong rotation now does not necessarily imply its absence in the past. And if rotation existed in the early universe, it could have influenced processes at a time when the universe was far more sensitive to initial conditions. Now, consider the role of initial conditions more carefully. Cosmology relies on a model of the universe's beginning, often described as a hot, dense state, followed by rapid expansion. But this model does not uniquely determine all properties of the universe. Certain features, like the exact distribution of fluctuations or the presence of rotation, must be specified as initial inputs. Why those inputs take the values they do is one of the deepest open questions in physics. Some approaches attempt to derive initial conditions from deeper principles, possibly involving quantum gravity or multiverse scenarios. Others treat them as empirical facts to be measured and constrained. Rotation sits in this uncertain space. It is not forbidden, it is not required, it is simply a possibility that must be tested against observation. There's also a geometric perspective that sharpens the question. In relativity, space-time can be decomposed into different properties: expansion, shear, and rotation. Expansion describes how distances grow. Shear describes how shapes distort. Rotation describes how local frames twist. The standard cosmological model includes expansion and allows small shear in certain contexts, but typically assumes zero rotation on large scales. Allowing rotation adds another degree of freedom to the model. This makes the mathematics more complex, but also more general. From this perspective, asking whether the universe rotates is equivalent to asking whether one of the fundamental degrees of freedom of spacetime is non-zero. It is a question about the full structure of the metric, not just about motion within space. Now we reach a point where the discussion intersects with the limits of measurement. To detect or constrain cosmic rotation, we rely on extremely precise observations of light, matter, and their interactions across vast distances. These measurements are influenced by many factors: instrument sensitivity, astrophysical processes, and statistical uncertainties. Separating a tiny rotational signal from all other effects is extraordinarily challenging. Yet progress continues. New observations of the cosmic microwave background, improved galaxy surveys, and more sensitive instruments are steadily refining our understanding. Each improvement tightens the constraints, narrowing the range of possible rotation. This is how physics advances, not by sudden leaps to certainty, but by gradually reducing the space of possibilities. And still, the conceptual question remains unresolved. Even if we were to detect a small rotation, how would we interpret it? Would it be a relic of the universe's initial state? A consequence of deeper laws we do not yet understand? Or a sign that our current models are incomplete? Each possibility leads in a different direction. One points backward toward the origin of the universe. Another points downward toward more fundamental physics. The third points outward toward new frameworks that extend beyond current theories. At this stage, the original question has evolved into something far more intricate. We began by asking whether the universe rotates. Now we are confronting the possibility that rotation, symmetry, initial conditions, and the structure of space-time are all interconnected pieces of a larger puzzle. And that puzzle is not just about motion. It is about the deepest properties of reality: how space is structured, how time behaves, and how the universe came to be the way it is. If rotation can exist as a property of spacetime, and if even a tiny amount of it could survive from the earliest moments of the universe, then it raises a deeper question, one that goes beyond geometry and enters the nature of time itself. Because time in physics is not just a parameter we measure with clocks. It has direction. There's a difference between past and future. You remember yesterday, not tomorrow. Causes come before effects. Entropy increases. This direction is often called the arrow of time. But here's the problem. The fundamental laws of physics, whether in classical mechanics, electromagnetism, or even much of quantum theory, do not strongly prefer a direction of time. The equations mostly work the same whether time moves forward or backward. So where does the arrow come from? The standard answer is entropy. Systems evolve from ordered states to disordered ones. The early universe had extremely low entropy, and as it expanded, entropy increased, giving time its direction. But that explanation leaves something open. Why did the universe start in such a low entropy state? And could rotation have played a role? In a rotating spacetime, the structure of time is not uniform. The tilt of spacetime, the way time mixes with spatial directions, can vary depending on position and direction.
This is not just an abstract statement. In extreme cases, like the one proposed by Kurt Gödel, the tilt becomes so strong that paths through spacetime can loop back into the past. The distinction between forward and backward in time becomes less rigid. Now imagine a much weaker version of this. Not strong enough to create time loops, but enough to introduce a slight directional bias in how time behaves across the universe. Such a bias could, in principle, influence how entropy evolves. It would not reverse the arrow of time, but it might shape its uniformity, perhaps making time's flow ever so slightly different in different directions or regions. This is speculative, but it connects two deep ideas, the geometry of spacetime and the thermodynamic arrow of time. And it suggests that time's direction might not be entirely independent of the universe's large-scale structure. Now move one layer deeper into quantum physics. At the quantum level, the vacuum is not empty. It's filled with fluctuations, temporary appearances of particles and fields that constantly emerge and disappear. These fluctuations are influenced by the structure of spacetime. If spacetime carries a global rotation, even a minute one, then the quantum vacuum is not perfectly isotropic. It has a subtle orientation built into it. This could, in principle, affect how fluctuations behave. Over vast timescales, these tiny differences might accumulate. They could influence the distribution of energy, the formation of structure, or even the statistical properties of quantum processes. We do not yet have a complete theory that fully describes quantum fields in a globally rotating cosmological spacetime. The closest framework we have, quantum field theory in curved spacetime, allows us to explore partial effects, but not the full picture. This is where the absence of a complete theory of quantum gravity becomes significant, because rotation is not just about motion, it's about the structure of spacetime itself, and spacetime at the smallest scales is expected to have quantum properties. So the question becomes even more profound. If the universe has a built-in rotation, does that rotation persist all the way down to the quantum level? And if it does, could it influence the very processes that give rise to particles and forces? There's another angle that connects rotation with information. Modern physics increasingly treats information as a fundamental concept. Black holes, for example, are not just gravitational objects, they're also information systems. Their entropy is proportional to the area of their event horizons, and their behavior raises deep questions about how information is stored and preserved. Rotation plays a role here as well. Rotating black holes have more complex structures than non-rotating ones. They possess regions where spacetime is so strongly dragged that all motion is forced to follow their rotation. These regions affect how information flows and how energy can be extracted. Now scale this idea up. If the entire universe has a rotational component, then information flow across spacetime could, in principle, be influenced by that structure. Not in an obvious way, but in subtle patterns, how correlations propagate, how signals disperse, how coherence is maintained or lost. This is something we can't currently measure directly, but it highlights a recurring theme. Rotation is not isolated. It connects to geometry, to time, to quantum behavior, and to information. At this point, we can step back and look at the overall structure of the idea. We started with motion, whether the universe spins.
We moved into geometry, how spacetime could encode rotation. We explored observation, how light and matter might reveal it. We connected it to time, how rotation could influence causality and entropy. We extended it to quantum physics, how the vacuum itself might carry traces of rotation. And now we see that all of these are not separate threads. They are different perspectives on the same underlying question. Does the universe have a hidden structure that breaks perfect symmetry? There is one more conceptual challenge that remains. Even if the universe rotates, even if we could measure it with infinite precision, there is a limit to what we can know from inside the system. All observations are internal. All measurements are relational. We never step outside the universe to compare it with something else. This creates a kind of epistemic boundary, a limit on how rotation can be defined and detected. In some sense, the question, is the universe rotating, may not have a single absolute answer. It may depend on how we define rotation within the framework of our theories.
Different formulations of physics might describe the same reality in different ways, some attributing rotation to spacetime, others absorbing it into coordinate choices or initial conditions. This does not make the question meaningless, it makes it deeper. It means understanding rotation requires not just measurement, but interpretation. And this leads to a final shift in perspective. Instead of asking whether the universe rotates in a classical sense, we can ask, does the universe contain a fundamental asymmetry that behaves like rotation? Because that is ultimately what we are probing, a deviation from perfect symmetry, encoded in the structure of spacetime and reflected in the behavior of everything within it. If such an asymmetry exists, it would be one of the most subtle features of reality, not something we see directly, but something we infer from the smallest inconsistencies in the largest patterns. At this stage, we have moved from concrete physics into the edge of what can currently be understood. The question is no longer just scientific, it is conceptual. It touches on how we define motion, how we interpret symmetry, and how we extract meaning from observations made entirely within the system we are trying to understand. And yet, despite all this depth, the original curiosity remains intact. What if the universe is rotating and we are simply too embedded within it to notice? In standard physics, space-time is treated as a smooth continuum. It can bend, stretch, and twist, but it is still a continuous geometric object. Rotation in this picture is a property of that geometry, encoded in how local frames evolve and how paths curve. But many approaches to fundamental physics suggest that spacetime may not be continuous at the deepest level. It may be emergent, built from more primitive ingredients, discrete structures, quantum states, or networks of information. If that is true, then rotation is no longer just a geometric feature. It becomes something that must be defined in terms of these underlying elements. And that changes the question again. Instead of asking whether spacetime rotates, we ask whether the building blocks of spacetime carry something equivalent to angular momentum. In some approaches to quantum gravity, spacetime is described in terms of discrete structures, networks where nodes and links encode relationships rather than positions in a smooth background. Geometry emerges from how these elements are connected. Within such frameworks, rotation would not appear as a continuous twist, but as a global property of the network, a kind of topological feature that cannot be removed by local changes. This is a very different kind of rotation. It is not something you can gradually turn off by reducing a parameter. It is something embedded in the global structure, more like a knot than a spin. If the universe had such a property, it would mean that rotation is not just an initial condition or a dynamical effect, but a fundamental aspect of how spacetime is constructed.
There's another perspective that comes from the study of symmetries at the quantum level. In quantum theory, symmetries are deeply connected to conservation laws. Rotational symmetry, for example, is tied to the conservation of angular momentum. But if the universe as a whole breaks perfect rotational symmetry, if it has a preferred direction, then the global conservation laws must be interpreted carefully. Locally, angular momentum can still be conserved in interactions, but globally, the definition of total angular momentum becomes subtle, especially in an expanding and possibly anisotropic spacetime. This raises a technical but important issue. In a universe that is not perfectly symmetric, some quantities we take for granted may not be globally well-defined. Rotation, in this sense, becomes a property that exists without a simple global value. Now consider how this interacts with the expansion of the universe. Expansion stretches spacetime, increasing distances between galaxies. If rotation is present, it must evolve alongside this expansion. The equations governing such behavior show that rotational effects tend to dilute over time. As the universe grows, the influence of any initial rotation spreads out, becoming less significant locally. But dilution is not elimination. A small initial rotation could persist indefinitely, always present but increasingly subtle. Its effects would be most pronounced in the early universe, when distances were smaller and interactions more tightly coupled.
This suggests a strategy for understanding rotation. Look not only at the present universe, but at its earliest observable stages. The cosmic microwave background provides one such window, but there are others, such as the distribution of primordial gravitational waves. Gravitational waves are ripples in space-time itself. They carry information about the dynamics of the early universe, including any anisotropies or rotational features. A rotating early universe could, in principle, produce distinctive patterns in the spectrum or polarization of these waves. Detecting such patterns is extremely challenging, but future experiments aim to reach the required sensitivity. There is also a connection to topology, the global shape of the universe. Topology is not about local geometry, but about how space is connected on the largest scales. A universe can be finite or infinite, simply connected or multiply connected, without changing its local physics. In some topological models, global properties can mimic the effects of rotation. For example, a universe with certain boundary conditions or identifications might produce directional patterns in observations, even if spacetime is locally non-rotating. This complicates interpretation. If we detect a preferred direction, is it due to rotation, or is it due to topology, or something else entirely? Disentangling these possibilities requires combining multiple lines of evidence: geometry, dynamics, and observation. Now move toward an even deeper layer, the relationship between rotation and the concept of time ordering. In most physical theories, events are ordered in time in a consistent way. Even in relativity, where simultaneity is relative, causality imposes a structure. Events influence others within their future light cones. Rotation, especially in extreme cases, can distort this structure. In Gödel-like spacetimes, the light cones tilt in such a way that closed time-like curves become possible. But even without reaching that extreme, a small rotational component can alter the orientation of light cones across spacetime. This means that the direction of time, as experienced locally, could vary slightly depending on position and direction. Not enough to be noticed in everyday life, but enough to have theoretical significance. It suggests that time is not just a scalar parameter flowing uniformly, but a direction embedded in a geometric structure that can, in principle, twist. There's a subtle implication here. If the direction of time is influenced by spacetime geometry, and if that geometry includes rotation, then the arrow of time might not be purely thermodynamic, it might have a geometric component. This does not replace the role of entropy, but it complements it. The increase of entropy could be guided, in part, by the underlying structure of spacetime. This idea is not established, but it illustrates how deeply interconnected these concepts are. At this depth, the distinction between different areas of physics begins to blur. Cosmology, general relativity, quantum theory, and thermodynamics are no longer separate domains. They become different aspects of a single unified problem, understanding the structure and behavior of the universe at all scales. Rotation is one thread in this larger tapestry. It starts as a question about motion, but it leads into questions about symmetry, geometry, information, and the nature of time. There is one more direction to explore, one that involves the limits of observation itself. All measurements we make are based on signals that travel at finite speed, primarily light. This means that when we observe distant regions of the universe, we are seeing them as they were in the past. The observable universe is not the entire universe. It is a region bounded by how far light has had time to travel since the beginning. If the universe has a global rotational structure, it might extend beyond what we can observe. Our measurements would then capture only a portion of that structure. This introduces an unavoidable limitation. Even with perfect instruments, we cannot access information beyond the observable horizon. Any conclusions about global rotation must be inferred from incomplete data. This does not make the effort meaningless. It defines the scope of what can be known. Now the question takes on its most refined form. Not simply whether the universe rotates, not even whether spacetime has a twist, but whether the observable patterns we detect, light, matter, radiation, contain consistent, measurable deviations from perfect symmetry that can only be explained by a fundamental rotational structure. And if they do, whether that structure originates from initial conditions, deeper laws, or emergent properties of a more fundamental theory. At this level, the problem is no longer about a single answer. It is about mapping the space of possibilities and narrowing it through theory and observation. Each constraint, each measurement, each refinement of our models reduces uncertainty. But it also reveals new layers of complexity, new connections that were not visible before. And through all of this, the original intuition remains quietly present. You're sitting still, reading this, yet you're on a planet that spins, orbiting a star that moves through a galaxy that drifts through an expanding universe. And beyond all of that, there may be a deeper motion, not of objects through space, but of space itself. A motion that cannot be seen directly, only inferred. A motion that, if it exists, is woven into the structure of reality at every scale. One of the most powerful modern ideas in theoretical physics is that space-time might not be fundamental. Instead, it could arise from more basic ingredients, often described in terms of information, quantum states, or entanglement. In this picture, geometry is not primary. It is constructed. Distances, curvature, even the flow of time may emerge from how underlying degrees of freedom are organized. And if that is true, then rotation, like curvature, must also emerge from that structure. This shifts the meaning of the question again.
Instead of asking whether space-time rotates, we ask whether the underlying information structure of the universe contains a kind of asymmetry that manifests as rotation when viewed at large scales. One framework where this idea becomes concrete is holography. In holographic theories, the physics inside a region of space can be described by information encoded on its boundary. The most well-known realization of this idea is the ADS-CFT correspondence, where a gravitational theory in a higher dimensional space is equivalent to a non-gravitational theory on its lower dimensional boundary. In such a framework, properties like rotation in the bulk spacetime correspond to specific features in the boundary theory. This means that a rotating universe at a fundamental level might be described as a particular pattern of information flow on a lower dimensional structure. Rotation becomes translation. Movement in one description corresponds to a different kind of transformation in another. And this suggests something profound. What we perceive as a global rotation of spacetime might be, in a deeper description, a property of how information is organized and evolves. Now consider horizons. The observable universe is bounded by a horizon, the limit beyond which light has not had time to reach us. This horizon is not just a practical boundary, it has physical properties. It has an associated temperature, entropy, and information content. Horizons behave in many ways like thermodynamic systems. If the universe has a rotational component, even a tiny one, it could influence the structure of this horizon. The distribution of information, the flow of energy, and the correlations across the boundary might carry subtle imprints of that rotation. This is not something we can directly observe yet, but it connects rotation to one of the deepest ideas in modern physics, that spacetime, gravity, and thermodynamics are intimately linked. There is also a connection to the idea of emergent time. In some approaches, time itself is not fundamental, but arises from more basic relations such as entanglement or the ordering of quantum states. If time emerges, then its direction, its flow, and its uniformity are not guaranteed. They are properties that depend on the underlying structure. Now bring rotation into this. If the underlying structure has an asymmetry, something that, when coarse-grained, appears as a twist in spacetime, then the emergence of time could carry traces of that asymmetry. This means that the arrow of time, the consistency of causality, and the geometry of spacetime might all be linked at a level deeper than current theories fully capture. At this depth, the original question has transformed almost completely. Is the universe rotating is no longer just a question of motion. It is a question of whether reality contains a built-in asymmetry that manifests across multiple layers. In geometry, as a twist of spacetime, in observation, as subtle directional patterns, in dynamics, as tiny biases in motion and structure, in quantum theory, as anisotropies and fluctuations,
in information as patterns in how the universe encodes itself. Each layer offers a different perspective, but they all point toward the same possibility, that perfect symmetry may not be exact. And yet, despite all this depth, physics remains grounded in observation. Theories can suggest, extend, and generalize, but they must ultimately confront data. So far, every precise measurement, from the cosmic microwave background to large-scale galaxy surveys, tells a consistent story. If the universe rotates, it does so extremely slowly, so slowly that its effects are nearly indistinguishable from perfect symmetry. But nearly is not exactly. And in physics, the difference between those two words can define entire revolutions. Future observations may push this boundary further. More sensitive measurements of cosmic radiation, deeper galaxy surveys, and the detection of primordial gravitational waves could reveal patterns that are currently hidden. They may confirm that the universe is effectively non-rotating. Or they may uncover a small but undeniable asymmetry, a signal that something subtle is present. Either outcome is significant, because confirming perfect symmetry would reinforce one of the central assumptions of modern cosmology, and detecting even the slightest rotation would force us to rethink it. Now step back one final time. You began with a simple intuition. Everything moves. Earth spins, stars orbit, galaxies rotate. So it feels natural to ask whether this pattern continues upward, whether the universe itself participates in this hierarchy of motion. Physics does not dismiss that intuition. It refines it. It shows that the answer is not straightforward, because the universe is not an object inside a larger space. It is the stage on which all motion occurs. And yet, within that stage, the laws of physics allow for something remarkable. Space itself can carry motion. Time itself can be shaped by geometry. And the universe can, in principle, contain a hidden twist that affects everything within it. So where does this leave us? Not with a simple yes or no, but with a deeper understanding of the question. If the universe is rotating, it is not spinning in the way everyday objects spin. It is not turning relative to something outside. It is not something you could observe from a distance. It would be a property woven into the fabric of spacetime itself, subtle, pervasive, and difficult to detect. And if it is not rotating, then that absence is just as meaningful. It would tell us that the universe, at the largest scales, is extraordinarily symmetrical, more balanced than almost anything we encounter in nature. In the end, the question remains open, but transformed. Not just, is the universe rotating, but does reality, at its deepest level, contain a direction, an intrinsic feature that distinguishes one orientation from another? And if it does, how is that direction encoded in the laws that govern everything we see? You are here, inside this universe, trying to understand it from within. Every measurement you make, every theory you build, is part of the system you are studying. And somewhere in that system, hidden in light, in structure, in the geometry of spacetime itself, may lie the answer. Not obvious, not direct, but waiting to be uncovered through the patterns it leaves behind.